Hi, I'm Austin Hedges. I'm a physics major here at Longwood University, and I'm presenting about a summer research internship I did at Hampton University in the summer of 2019. And so this project was about making artificial CIPS data with a generative adversarial neural network, and I'll get into what all of that means in this presentation. Um, this was a project done along with another undergraduate student named Joe Mustachio. He is a student at Virginia Commonwealth University, and he and I worked under Dr. John McNabb at Hampton University in the Department of Atmospheric and Planetary Sciences. Um, so this project is kind of a mix of a lot of different areas, a lot of computer science, atmospheric science. It was really quite a fun experience. I'm glad I got to do it. I had a lot of fun with this project, and I learned a lot. So, and it's something I don't get to talk about too often. I get to talk about it, but I don't get to go super in depth about it. So I'm really excited to be presenting today about this. So I hope you enjoy. Um, of course, if you have any questions, please comment on this presentation. Some of these things can be kind of difficult to explain, so if there's something that you don't understand, just comment your question. I'll do my best to answer. Um, yeah, so I'll start off with a bit of an introduction, kind of some background about what this project was about. So this project was studying these types of clouds called polar mesospheric clouds, and these are the highest clouds on Earth at altitudes of around 82 kilometers, and they're above the north and south poles. And they are around the mesopause, which is the top of the mesosphere. So these clouds are thin ice clouds. One theory is that, so for ice to form, it needs something to nucleate around. Typically that's dust down here. But up there's not as much stuff, right? Atmosphere's thinner. One theory states that ice could nucleate around meteoric smoke from meteors entering the atmosphere. And in order for this ice to form, it also needs water up there. So the water gets there through the oxidation of methane in the stratosphere. Um, and so one thing that's kind of interesting about PMCs is that their first observation was in 1885, so not that long ago. They're quite a recent phenomenon. And so since they form through the water is from the oxidation of methane. The more methane there is, the more these clouds form. And so these clouds are actually forming more and more often due to climate change from pollution and other industrial factors that release methane into the atmosphere. So the observation of PMCs is used to actually kind of study climate change, because you have methane in the upper atmosphere from this. So these clouds are studied using a NASA satellite called AIM, which stands for Aeronomy of Ice in the Mesosphere. This is a satellite that has been studying these clouds since 2007. In 2007, it was launched aboard a Pegasus XL rocket, which was carried underneath a Lockheed L-1011, which is a type of aircraft that was commonly used for cargo and passenger flights. So this plane flew up to an altitude, dropped the rocket, and then the rocket put this satellite into a polar sun-synchronous orbit at an altitude around 600 kilometers. And a sun-synchronous orbit means that it passes over the same point, or it passes over a given point at the same time each day. So this satellite has 3 instruments that are used to study PMCs. These instruments are SOFI, CDE, and CIPS. SOFI stands for Solar Occultation for Ice Experiment. This is a camera that looks through the atmosphere into the sun to study the constituents of the atmosphere at this altitude. And looking through the atmosphere into the sun gives a very high vertical resolution. I believe the resolution of this is around 1 kilometer, which is quite good. CDE stands for Cosmic Dust Experiment. What this instrument did was it would measure the flux of cosmic dust in this coming into the atmosphere. So if it's coming through 600 kilometers, it would end up in the atmosphere, because that was one theory that the ice nucleated around cosmic dust. This instrument was, I believe, was made out of a thin plastic type film that would measure the flux of cosmic dust. I don't think they run this instrument anymore. I don't think it really made any significant measurements when it was being run. And finally, we have CIPS, which stands for Cloud Imaging and Particle Size. And this is a set of cameras that image these clouds. And so this is the instrument that I primarily was focused on. And so it consists of 4 nadir-facing cameras, which means they look straight down at the clouds. And in this image of the satellite, you can see these 2 things that are sticking on the bottom. Those are 2 of the cameras, 2 of CIPS cameras. And these cameras image in the ultraviolet, centered at 265 nanometers with a 15 nanometer passband. And that means that the images are, that the clouds are being imaged at 265 plus or minus 7.5 nanometers. And so these cameras are imaging the albedo of the clouds. So a higher albedo means more light is being reflected. That means there's a cloud there. If there's a low albedo, means there's no cloud there. And so measuring the albedo difference can kind of show where clouds are and the structures that are present within these clouds. So when these 4 cameras take an image, you can project their image onto the surface of the Earth, and you get this kind of a bow tie shape that you see here in Figure 2a. And this bow tie shape, they take the image with all 4 cameras at the same time, and they'll take multiple images throughout an orbit. And if you combine these bow tie shaped images, you get an orbital strip. And throughout the day, as the orbit progresses around Earth, you can combine these strips into a larger picture, which will show you a picture of the entire pole, so you can see the large polar mesospheric cloud structure. So we wanted to apply neural networks to data from CIPS, and so just kind of want to give a brief, I guess maybe not brief, but I want to describe what a neural network is. It's a type of computer program that actually mimics how the brain learns information. And these programs are really good at recognizing patterns and classifying them, as well as making predictions. So kind of the structure of a neural network is you have different layers of neurons. And so this image here in Figure 2b is a good representation of a generic neural network, a very simple one. So you start off with an input layer, and you input your data through there, and then you have these connections here, and these connections have something called a weight associated with them. That's just a number. And then, so you have the number that goes through here, and each neuron is connected to every neuron in the next layer for this type of neural network. And then these neurons will have another number within them. And so the way that you actually calculate the number in a certain neuron, in this hidden layer, for example, is you would take the weighted sum of all the neurons in the previous layer, along with their associated weights, to get the number in that neuron. So what you do when you have a neural network, you want to train it to be able to learn like a brain. And when you first create the neural network, the numbers that are associated with the weights are going to be random. They're not going to be something that will lead to a correct answer. And then in addition to these weights, the neurons also have something called a bias along with them. And so when you want to know the value of a given neuron, you take the weighted sum of all the previous neurons and their weights, and you add this bias to it, and that kind of helps. That actually helps with the neural network's learning process. And so when you want to train a neural network to be able to identify images, for example, you might build a neural network to distinguish between pictures of dogs and cats. So you would give it a picture of a dog, and you would have a label associated with that says dog. And for a cat, it would say cat. And so what you do is you give a neural network a piece of data with the correct label. Initially, that piece of data will run through and lead to most likely an incorrect result. And then you tell it what the label was, and it will go back and it will adjust its weights and biases in order to get to the correct output. So in order to do this, there are a few things that must happen first. When a piece of data is sent through here, you will get an output. So for example, for the dog and cat example, you'd have 2 output neurons, one associated with dog and one associated with cat. And in each neuron, you're going to get a number. And whichever number is larger it's going to be its choice, I guess. So if the dog's number is larger, then the network is saying that it thinks it's a dog. And so in order to calculate how incorrect a given output is, you use something called a loss function, and I'll get more into what that looks like later. So once it calculates the loss, if the loss is large, it needs to make big changes. If it's small loss, meaning it's closer to being correct, then it'll make smaller changes. And then it does this thing called back propagation, where it goes back through the connections that were used to get to a given output, and it will tweak the weights and biases to get more correct outputs. And a big benefit to neural networks, something that's very good about them, is they learn from both success and failure. And so if you get a correct output, then the connections that led to that correct output are strengthened. If you get an incorrect output, the connections that led to that output are weakened. And so these are especially really good for recognizing patterns and making predictions, and that's what we are doing in this project. So for this project, we used a certain type of a neural network called a Generative Adversarial Network. And so these were developed in 2014 by Dr. Goodfellow and his colleagues at University of Montreal. So they're quite a recent invention. And that was something that was really fun for this project, was this is something that's very new. GANs are something that have just come out, and the applications to them are not fully known, so people are discovering new applications for them. And no one else had ever applied a GAN to CIPS data, so what we were doing was original research, which was quite fun. And so this neural network framework consists of two neural networks, and these neural networks actually kind of compete against each other. And these two neural networks are, one is a generator, which takes in just random noise, just random data, and manipulates that data into looking like a real image. Of course, it's not actually a real image, but it tries to make it look like a real one. And then you have the other network is called the discriminator, and that takes in generator images as well as real images and determines if a given image is real or not. So the generator will make fake images, the discriminator will take those fake images as well as real images, and it'll learn to distinguish between the two. So in the beginning, the generator network will just be outputting random noise because its weights and biases are not going to be leading it to making anything that looks real. So you take that random noise and you feed it into the discriminator along with real images, and the discriminator will get good at determining the difference between these generated images and real images. And once an discriminator is confident in its ability to distinguish between real and fake images, you then use the model from the discriminator to train the generator. So the generator is trained based off of how good at tricking the discriminator it is. And so that's what it's being trained off of the model. And so in the beginning, the generator is not really going to trick the discriminator a whole lot because it's just going to be random noise, which look nothing like real images. But over time, you swap between generator and discriminator multiple times, and over these iterations, you'll end up with a generator that generates really good, convincing images. And that's the goal of a GAN, is to make convincing generated images. And so for CIPS data, this can be quite useful, actually, having fake images. Usually, the idea of fake data is kind of scary. You don't want to mess around with fake data, but for neural network applications, it actually can be quite useful. Because when you're training a neural network, you pass in images into the network. And once you've passed an image through the network for training, you can't use that image anymore for training because there's the possibility that it will it'll identify specific images instead of generalities. You want to be able to identify things in general. So once an image has been passed through a network, that image is no longer useful. And so if you're working with a small data set, you can't use all your images because then you have nothing else to use. So having fake images can actually be quite useful for training other neural networks, and that's kind of the goal of this project and why you would want to build a GAN for CIPS images. But in the past, the reason why GANs were invented is because in the past, discriminators have been much more powerful and more efficient than generators. Old generated images just look nothing like real life and were quite weird. And actually, if you look up images that were generated by GANs, they are quite convincing. I know there's a website, I think it's something like thispersonisnotreal.com, something like that, where it's just a picture purely generated by a GAN from random noise, and it looks like a real person. You would have no idea that it's not a real image. So these can be quite powerful. And this here is a good diagram of what a GAN is doing. So here on the left, the generator starts off with random noise. It generates fake samples, fake images in my case. and then these fake images are passed along with real images into the discriminator, and decides, it trains to distinguish between whether it's real or not, and then the discriminator's model is then used to train the generator, and it gets better at tricking the discriminator. So you pass back and forth, and over time you'll end up with a generator that can generate very realistic, convincing images. So for our project, our GAN was written in a programming language called Python, and we used a machine learning library called PyTorch, which was developed in 2016 by Facebook, actually. So that's also something that's very recent. PyTorch is quite new, and it's good for allowing the user to write neural networks. If you were to write it from scratch, it would be very difficult, so it gives you the ability to write networks. It's a little more simpler to write and more powerful. And that includes making the hidden layers like we have over here in this diagram. You create your layers and your types of layers, and that's what we use PyTorch for. So I wrote the discriminator for this project, so I'm going to be focusing more on that and how it worked. My partner Joe wrote the generator, and then he and I went back and forth, and that's how we were able to generate our images. So for the discriminator, it took in the fake images from the generator, but also needed real images. So for these real images, we used the PY camera from AIM, which over here is this one right here, this yellow one. So we took in thousands of images from AIM, as well as thousands of generated images, in order to train the discriminator for each iteration. And so in our diagram of a neural network, you can see the input layer is just a one-dimensional layer of neurons, and we're starting off with a two-dimensional image. So we need to squash that into a one-dimensional tensor. So that's the first thing we do, is we squash the image into a one-dimensional tensor, which is just going to be a list of values for the pixels. And since it's measuring albedo, it's basically just telling you how bright the cloud is there, how much is being reflected. So for a given pixel, you'll have some decimal number that'll be telling you how bright that pixel is. So the discriminator and generator were built with multiple types of layers, as well as multiple layers. So the discriminator was built using a few different types of layers. One in particular was a convolutional layer, and in this one you have the two-dimensional image, and you have a square window that scans over the image's pixels. And if we look here in this figure on the left, in figure 4a, this is kind of a good representation of what's happening. So you can imagine that this table here, I, is like an image. K is like your window. And so the way it works is, over here in I, for each of these pixels, in this example, it's just 0 and 1. For us, it's some decimal number that represents how bright the pixel is. But for K, you're going to have either zeros, ones, or negative ones. And basically, what's happening in the window is it's detecting edges on the image. And that's really important, especially for clouds, because you want to be able to detect where the clouds, what shapes their structures kind of have and where they are. And being able to detect edges is something that's important for being able to identify clouds. So what's happening here is this window will start off, it'll scan over, move over one pixel, scan, move over one pixel, scan, and it'll move down and do the same thing. And so what happens when it's, for example, if you're over this 3x3 matrix right here in the image, what you're really doing is just you're multiplying the two matrices, and then you're adding up all the numbers in that resulting matrix. And so, for example, this matrix here just has ones in the diagonals, and I believe that's the one that was the one that was used in the discriminator. It was that type of a matrix. That one just detects all types of edges. You can change this matrix here to detect top horizontal, bottom horizontal, left vertical, right vertical edges, different types of edges. But we just wanted to detect any type of edge in any direction, so that's what this matrix is used for. So you multiply this matrix by this matrix, and then you add up the values that result. So for example, for this one, if you multiply these over, you just get 4, and then you scan over and you continue and do the same thing. And so this is really good at just detecting edges, detecting structure, which is really important for detecting clouds. And that's what the discriminator needs to do, is detect whether or not there's a cloud in the image. In addition to convolutional layers, often when you use a convolutional layer, you'll also use a pooling layer, which is what I used in discriminator. And what happens in this is you actually downsample the image to a lower resolution by combining groups of pixels. And this allows the network to identify structures regardless of location. It's really important for the network to be able to identify structures in general rather than specific location. If it's seeing something like, oh, the top left of these images have a line here, you don't want to be able to, you don't want it to be making to recognize patterns purely based off location. You want to be able to recognize it anywhere. So that's something that's useful with pooling layers. And in the discriminator, I used a type of layer called a max pooling layer. And so this is a good diagram showing what's happening here. For this one, the kernel is 2 by 2, which means it's looking at a 2 by 2 area. The stride is 2 in the horizontal and 2 in the vertical, so it'll look at a 2 by 2 and then step over 2, look at the next 2 by 2 and then go down and do the same thing. And for a max pooling layer, it is just looking at the maximum value in that given kernel. So for this one it's 9, and that's why the 9 comes out over here. For this one it's 7, and so on. So this downsamples the image and just looks at the maximum value of the pixel. So the discriminator used these types of layers in addition to the typical linear layers that you would have, like in this figure down here in this diagram. Here's just a linear layer where each neuron is connected to every neuron in the previous layer as well as in the next layer. So an important thing that you need to have in a neural network is something called an activation function. And this will actually adjust the value inside of a neuron. So that neuron holds a value that is the weighted sum of the previous neurons plus the bias that the neuron holds. And so you could just have that number and just not use any activation function. But I know this is something that isn't really recommended for neural networks. I believe that if you use no activation functions and you have a bunch of linear layers, then it essentially is like squashing into one layer. I'm not sure if that's exactly the best way to describe it, but essentially having an activation function will help the network to be more efficient and to be better at going towards correct results. And so you take that weighted sum plus the bias, the value of the neuron, and you pass it through a certain type of activation function. And these functions were designed to kind of mimic how the brain's neurons will activate with different stimuli. And it's kind of interesting to see how that it's mimicking something biological, and it actually works quite well in a computational sense. So with the pooling and convolutional layers that I used, it's quite common to use the ReLU function. And this is a really simple function. And all it does, it takes the max between 0 and that activation that you're passing into it. That's what the 0 and the x would be your activation. So if the activation is negative, it just outputs 0. So it just cancels out all negative outputs, or all negative activations. And then if it's 0 or greater than 0, it just returns that same number. That's what, this is kind of a good graph showing what it looks like. Any negative value just goes 0. Anything 0 positive just stays as is. And having a very simple function helps to reduce the time necessary to train a network, and then passing certain values to 0 helps to make the network more concise and reduce noise, so that way you don't have a ton of outputs leading to a bunch of, you don't want to have neurons that are unused just kind of sitting there, so you just send to 0 so that nothing can pass through there. So in order for the discriminator to be able to identify real and fake images, like I mentioned earlier, it needs to use a loss function to calculate how wrong the output is. So the loss function that I use is called a cross-entropy loss function, and its formula is here. C prime is the number of classes for the output. So for this one, it's just 2 because you have either it's a real image or a fake image, so it's just 2 classes it can be. TI is the correct label, so for a generated image it's 0, for real image it's 1, and SI is the value for the given output neuron. And so the network then propagates back through the layers, and that's where it's going to be tweaking its weights and biases in order to lead to more correct outputs. So in order to know, right, like if you want to change a bunch of connections, you need to know which connections do I need to change first. So the network will calculate which connections will lead to a greater change in the correct direction. You want it to lead to correct outputs. So if there's a correct output, you want to strengthen the connections that led to a correct output, and you want to weaken connections that led to incorrect outputs. So this is done through something called stochastic gradient descent. That's what I used for this neural network, because your goal is to minimize the loss function. If your loss function is minimized, it means you're having the correct outputs, because loss function measures how wrong you are. So if the loss function is minimized, your outputs are correct. And so in order to minimize the loss function, you're going to do something called gradient descent. And gradient descent, in general, will just measure the gradient, or calculate the gradient of the entire loss function across all training iterations. And that will give you the shortest way down towards minimizing the loss function, but that requires a lot of computational power, because you're going across all training iterations, and that's thousands and thousands of images and thousands of processes that you have to calculate through. So we use something called stochastic gradient descent instead, which instead of taking all samples, it just takes some random samples, which reduces the computational power that's required. It also means it's a little bit less efficient, right? So if you look at this visual representation of this gradient descent, just a straight up gradient descent would just go straight from the outside to the minimum of the loss function. But that requires so much computational power, so you don't use that. That's not very common. And so when you're taking these random samples, certain samples will be more helpful or a little bit less helpful. So that's kind of why you get this stumbling type of effect, where it's not going straight down, but it kind of stumbles around, but it gets there eventually, and that's the important part, that it gets there, and then it's not using a ton of computational power. And so if you have a large gradient, you take a large step towards the minimum. If you have a small gradient, take a smaller step. And that's done to prevent from going past the loss function. If you take large steps all the time, you'll just run past it. If you take small steps, it'll take forever. So this is what you're doing to minimize the loss function and to lead to correct outputs. So through this process of backpropagation, you're tweaking your weights and biases to lead to more correct outputs. And that's kind of how the training process of a neural network works. So for this GAN in this project, we were able to get it through 6 iterations, swapping between the generator and discriminator. Of course we would have liked to do more than that, but this was an 8-week program over the summer, and we had to learn, we'd learn about PMCs, AIM, Python, PyTorch, Linux, neural networks, and GANs as well, and then write the whole thing. But we were able to prove that the GAN that we designed actually was functioning properly. And so these are these are some random images from the first 6 iterations. The 6 iterations that we were able to perform between the generator and discriminator. And of course the first iteration is just a random noise. That's what the generator starts off with, is random noise. And it's not going to know what to do with it, so it's just going to basically stay random. And then you take a bunch of those images and you pass them through the discriminator, and the discriminator gets pretty good at identifying that those are fake. Over here in figure 7G, we can see this is actually an image of a real cloud, so this is what you would want it to look like. And these are what the images that the discriminator takes in kind of look like. It'll take a lot of these pictures in, as well as a lot of the generated images. So then, in the second iteration, the generator seems to have realized that the discriminator is not very good with these vertical bars somehow. I mean, the thing that's kind of interesting about neural networks and GAN specifically is that I don't know what's actually going on within the network. It does its own thing, and it's figuring out how to trick the discriminator, and the discriminator is figuring out how to identify real images. So somehow the generator realized that the discriminator is not good at noticing these vertical bars, and you can see this persist throughout all the iterations. But over time, you can see, like in the fourth iteration, the discriminator got a little bit better, and so now the generator has to compensate by making the image is a little more smooth. The fifth iteration, something weird kind of happened. I'm not entirely sure what the generator was doing, but clearly that was working. Adding this horizontal bar and something here was tricking the discriminator, and then the discriminator figures that out, and the generator goes back to doing this type of thing. And you can see that, it's more smooth. It's not just random noise anymore. It's more smooth. But you can still see that there's something going on with these vertical bars. The discriminator is not very good at telling. Is not good at noticing these vertical bars, and that's likely due to the types of layers and the amount of layers that the discriminator has. And so, in order to improve this GAN, there are a few changes that are necessary. I think the important thing is that the important thing about this, though, is that the GAN is clearly working. Obviously, changes are happening between iterations, and that's kind of what we want to happen. I mean, this was a short program, so obviously we're not going to make a perfect GAN, but our goal was to get it working and to show that it is working. The generator is still easily fooling the discriminator, and so we need to kind of beef up the discriminator, especially. So we need different types of layers, some more layers most likely, and then you'd probably also have to beef up the generator as well, because if you just left the two networks as is and let them run, you'd probably get to a point where they just kind of stagnate and nothing really changes. And so you're going to have to make changes to make it actually look like real clouds. But I had a lot of fun with this program at Hampton University. It was a great experience, and I'd like to thank Joe Mustachio, my partner, who helped me work with this. He worked on the generator side while I was in the discriminator side. So he and I had to communicate a lot. We worked together all the time to build this and to get it running in time. I'd also like to thank Dr. McNabb from Hampton University. He was our research advisor. He had the idea to apply neural networks to AIM data, but it wasn't just a project that was handed to us. It was Joe and I coming up with our own ideas, and it really was original research. That was quite exciting, I think. I'd also like to thank Elliot Scheibin. He was a graduate student at Hampton University. He helped a lot, especially with some Python and PyTorch stuff, as well as neural networks in general. And of course, I'd like to thank NASA and the AIM mission team for making this possible. What they're doing is wonderful, and I mean, if we didn't have their data, we wouldn't be able to do any of the things that we did here. So if you're interested in reading some more about these things, I recommend some of these sources. These are really good sources. A lot of these are about polar mesospheric clouds as well as AIM, the satellite. Some of these are images as well, and some of these are about neural networks. And so one thing that was kind of cool at Hampton University, when Joe and I had finished our project, we actually presented in front of the Department of Atmospheric and Planetary Sciences, as well as some experts in the field, and that included the PI, the principal investigator of the AIM mission, and that is Dr. Russell. And so he wrote actually a lot of these papers that I cite. So that was quite fun to present to someone that's so important for the AIM mission. But if you're interested in learning more about PMCs and AIM, I strongly recommend some of these sources. If you want to learn more about neural networks, some of these sources are pretty good. These are going to be going super in-depth though. So if you kind of want to learn more about neural networks in general, I strongly recommend maybe finding some videos about them. I know there's a channel on YouTube, I think it's called 3 Blue 1 Brown, that makes some really good videos about the basics of neural networks if you're interested. And of course, if you have any questions, please feel free to comment on this presentation. If you have questions, or if you want maybe some more resources about this, you can email me. My email is austin.hedges@live.longwood.edu. But I hope you enjoyed my presentation. Of course, ask some questions, and have a great day. Thank you.